Given an algorithm, we'd like to find the time complexity t of n, giving us the exact number of steps required to complete the algorithm on an input of size n. But generally, it's too hard to do this. So we'd like to find the complexity category where t of n is order f of n. But that's generally too hard as well. So we'd like to at least find f of n where t of n is big O of f of n. To do that, we can make a few simplifications. So suppose our algorithm has a part that requires f of n steps and another part that takes g of n steps. If f of n is big O of g of n, but g of n is not big O of f of n, then the sum is big O of g of n. In other words, you can ignore f of n. We can interpret this as the algorithm having a fast part f of n and a slow part g of n, where the combination of fast and slow is slow. Let's prove this. Now remember, the purpose of proof is that proof reviews and reveals. It reviews things we should know, and sometimes it reveals new insights. Since f of n is big O of g of n, here's the review, then there is a c where for all sufficiently large n, f of n is less than or equal to c g of n. So let's go ahead and add g of n to both sides, which gives us, and we'll let c prime equal c plus 1, giving us, and so there is a c prime, where for all sufficiently large n, the sum is less than or equal to c prime g of n. And so the sum of f of n and g of n is big O of g of n. So we might try to estimate the big O of an algorithm which combines n log n and n squared steps. So remember, the order of n log n is less than the order of n squared. So n log n is big O of n squared, but n squared is not big O of n log n. And so we can ignore n log n. Consequently, the combined algorithm is big O of n squared. What if the two parts are both big O of the same function? If f of n and g of n are both big O of h of n, then their sum is big O of h of n as well. So we can add components that have the same big O. We can prove this, but we'll let you do that. So, for example, an algorithm has two parts requiring f of n and g of n steps. Let's estimate big O of the algorithm. Now, we note that 8n squared is big O of n cubed, but n cubed is not big O of n squared. So we can ignore the 8n squared and conclude that first function is big O of n cubed. Similarly, square root of n is big O of n cubed, but n cubed is not big O of square root n, so we can ignore square root n and conclude our second function is also big O of n cubed. And so both f and g are big O of n cubed, so their sum is big O of n cubed. Next, suppose an algorithm has to run a procedure with g of n steps a total of f of n times. Then the product is big O of the product. This might not seem useful, but we can use any f star g star where f of n is big O of f star and g of n is big O of g star. So suppose an algorithm has a subroutine that requires this many steps that must be run this many times. Let's estimate big O of the algorithm. So we note that f of n is big O of n to the fourth, and g of n is big O of n log n. So their product is big O of n to the fifth log n. This means that in general, if we want to find big O of an algorithm, we can break it into parts, find suitable big O for each part, and combine them. Let's estimate big O of the naive sort algorithm. justify our steps, and verify our result. The pseudocode for naive sort can be described as find the least element in the current list and remove it, putting it in our sorted list, and repeat for all elements. So suppose our list has n elements. To find the least element in a list of n elements requires making n minus 1 comparisons. But n minus 1 is big O of n, so finding the least element is big O of n. This step has to be repeated for each of the n elements, so that means that since we have to repeat this step n times, the naive sort has order n squared. In fact, we determined that the number of steps is actually n times n minus 1 over 2, which we can expand, and find that this is order n squared. And this leads to the most important question to ask. Will there be... Wait a minute. No, wrong slide. Can we do better? To answer that, we'll need to consider how to create algorithms. We'll take a look at that next.